with a 1 week, followed up with a 1 week circulation test. And before I jump into that, I just want to acknowledge the ID squared team. Lots of researchers here at Texas Tech. Is lots of great grad students and another professor, Dr. Kevin Wan, contributing to the efforts. And then Precise Downhole Solutions, Dan Keogh and Alexi over there were huge in getting the coiled tubing string deployed. Dana Jurek with Nubrex, doing some fiber optic sensing for us during the circulation test. Sven Hartwig and the Resman team, and Pete Rose helping with the tracers, as well as the Utah Forge team, with helping us come up and validate our execution plans, as well as Matt Becker and his CSUL Long Beach team, who we had projects back to back, and we partnered on some of this work. So with that, I'll assume most people have a familiarity with Utah Forge, but just in case you don't, a brief overview. In Milford, Utah, this star, there's a very steep geothermal gradient, and the DOE has funded an enhanced geothermal system demonstration project. And 2 wells have been drilled, deviated around 65 degrees, and over the sections where they're completed, and a reservoir temperature of around 400 to 425 degrees Fahrenheit. And then hydraulically fracture stimulated to connect the wells, and injection. The lower well is the injector, and the upper well is the producer. They're drilled right on top of each other, but just about 100 meters apart. And so we, as John mentioned, that I'm a part of a team called ID Squared, and our objectives are to characterize really the long-term heat sweep performance of the enhanced geothermal system. And kind of to get there, we need to characterize the number of flowing fracture pathways, and then the uniformity of the flow distribution between those pathways. And we look at that in kind of 2 ways. There's near well bore, but then within the fracture network as well. And then we want to estimate the heat exchange area. And to do that, we are employing a wide variety of diverse diagnostics, including chemical tracers, spinner flowmeter logging, and then a lot of our project depended on having distributed fiber optic sensing measurements. And the idea is, and now what we're really working to do is integrate our observations as well as the observations that have been made by other projects at Forge, to simulate the long-term heat extraction of this enhanced geothermal system and when thermal breakthrough might occur. So fiber optic measurements at Forge have been really vital. They've given us lots of great measurements, cement monitoring and characterizing how the cementing of the 16B well was done. They give us measurements of the geothermal gradient. They're used to kind of see frac stage zonal isolation and crosswell frac head identification. And so the perforation intervals on the 16B well were actually chosen. So the 16A was stimulated first, and where fiber optic distributed strain sensing indicated a fracture had intersected the well, that's how these perforation locations were chosen. And fiber has also been used for microseismic monitoring, and more. So we'd really like to have fiber optic cables in this system to help us, diagnose what's going on downhole. But one of the problems is there's been a history of fiber failures at not only Utah Forge, but in general in enhanced geothermal systems at these high temperatures. So Rice and Silixa had a team that deployed fibers clamped to the outside of the casing, and UT and Shell had fibers that were deployed that way as well. Some of those fibers lasted longer than others. Some of them made it, were able to sense during the stimulation of the wells. But by the time we were about 30 days in, or excuse me, about 10 days into the circulation test in August 2024, all the fibers had failed down along the completed interval of the 16B wellbore. And that's really, it was a shame for multiple reasons. And one of them being our project that was kind of starting in 2025 depended on having those measurements. The plot here I'm showing is called an OTDR trace, optical time domain reflectometry trace. You send a laser pulse down this fiber optic cable, and you detect the amplitude of the backscatter you get. And when that just completely falls off, this is just showing you don't have signal down in the well, and that could be due to a variety of reasons that we won't get into here. But let's just suffice to say that all the fibers were broken. And so we talked with really precise downhole solutions, and folks like them do a bunch of coiled tubing deployed fibers in SAGD, steam assisted gravity drainage applications in Canada. So they're used to deploying fibers and have high survivability in temperatures not too far off from what we're encountering in geothermal systems. And so our main thesis was, after these fibers failed, was maybe we can borrow some technology from Canada, where they've kind of figured out how to do these hot fiber optic deployments and then apply this to a geothermal system. And so some of the pros so here's a cross section of an 1.75 coiled tubing string, and you can see some 1/4-inch capillary tubes inside of there. And each side, inside these capillary tubes, is a fiber optic cable it's with a coating. It's got a outside diameter of a few hundred microns, so just barely thicker than a few strands of hair. So another neat technology that Precise has, and that they've shown in Canada, is this turnaround sub. So actually, two of these capillary tubings are connected at the bottom with this turnaround sub. So in case one of these fibers fails, you can actually inject liquid at high velocity down one of these capillary tubes, and then blow out or produce the fiber from out, and then redeploy a new fiber. You can inject in a new fiber. So these fibers are you have zero intervention fiber replacement options, and then this coiled tubing string can be run and deployed as needed. And another benefit of this is it's deployable in deviated wells or laterals without tractors. So there's tractoring technology is not maybe very mature in high temperature environments. And then other forms of tracers that you might, form of fiber optic deployment you might consider, like pumping down bare fiber. Those are not currently available at these geothermal temperatures either. So this really gave us a method for going forward at Forge. Some of the cons were, so you put this coiled tubing string inside of your casing, which reduces your annular flow area slightly. And then if you want to run anything else in the well, you have to pull this coiled tubing out. So if you want to run a wireline log or something, you would need to pull that out. Or if you, so there'll be more stimulations on the 16B, I think, that are planned. And so the coiled tubing will have to be pulled out for that. And then another con is that if you're trying to do distributed strain sensing and maybe see fracture dilation or contraction, you have decreased physical coupling to the formation. You're sensing more what's going on in the wellbore. Okay, so our objectives were to design and deploy an instrumented coiled tubing string in the 16B well. Basically, get fiber optic sensing back at Forge, and then obtain measurements from this coiled tubing and other diagnostics during a 1 week circulation test, so that we can characterize the fracture flowing pathways for long-term heat sweep efficiency simulations. And so I'll present today on the design and deployment of this coiled tubing string, and then also the preliminary results that we're seeing from this 1 week circulation test we did in August of 2025. All right, so starting off with the design of this instrumented coiled tubing string. At a high level, we knew we wanted to do both distributed acoustic, temperature, and strain sensing. With distributed acoustic sensing, the fiber acts like you have a microphone every meter along the whole wellbore, and we can pick up microseismic, flow noise. It's also sensitive to temperature changes as well. We wanted distributed temperature sensing. That's very useful for long-term, monitoring thermal breakthrough between the wells and geothermal gradient sensing, understanding what's going on with the flow, and then distributed strain sensing. I've just acknowledged in the previous slide that we have decreased physical coupling between the fiber and the formation, but past what we would really hoped to see is when we injected into this fracture system and the fracture started dilating, we hope to be able to detect where that was occurring. And so we wanted to try an experimental strain sensitive fiber that's completed a little differently than what's normally done in SAGD. And then we also wanted to have a bottom hole pressure and temperature gauge. So we have a total of 4 1/4-inch capillary tubes in our coiled tubing string. 3 of them are for fiber. One has a multi-mode fiber that's used for distributed temperature sensing, and the other one has a single mode fiber used for distributed acoustic sensing. And these are connected with a turnaround sub, so they can be retrieved if they fail and then redeployed. And then we also had a separate 1/4-inch capillary tube that we wanted to fill with a silicone gel to help enhance the strain transfer. And so we use that as our distributed strain sensing fiber. And then another 1/4-inch capillary tube contains the tech line for our bottom hole pressure and temperature sensor. So this is just another schematic showing that. So the design of the coiled tubing, we went with an 1 3/4 outside diameter coil, and that was based on a few things. One was the number of capillary tubes we had to fit inside of here. And then there were also mechanical deployment considerations. So they worked with a coiled tubing company to model the Utah Forge well trajectory, and could this coiled tubing actually be deployed to depth with the friction modeled. And then as well as, wall thickness, depending on the pressure rating the pressure we expected to see, and fluid exposures. One thing to note is that inside of the coil is not connected is not exposed to the wellbore fluids. So there's just air inside this coiled tubing string. And there's a ported bowl nose. We'll see a picture of it later, but that allows a connection to the bottom hole pressure sensor. But aside from that, there's no connection between the coil, the inside of the coil, and the external environment. And so that we've got a lot of strong protection for our fibers. Okay, so for the strain sensitive fiber, Precise conducted laboratory testing of different silicone gels. So the goals we were trying to make was, okay, we want if we have fractures dilating and that is causing a bit of stretch on the casing, we hope that frictional coupling with the coiled tubing and the capillary tubes might be able to pick the fiber might be able to pick up some strain through that. So we wanted a silicone gel to kind of couple the fiber to the capillary tube, but we didn't want too strong of a coupling so that it wouldn't fail. So they did experiments at various temperatures um, and with different gels to kind of try to find the sweet spot between allowing some slip, but also good strain transfer. Um, and so then we went and manufactured this coiled tubing string. And so this is a picture of a cutaway of it. You can see three of the capillary tubes inside of there. And this is a reel of about 10,500 feet of this 1 3/4 coiled tubing string. And at the end, you see this ported bull nose. That's where hydraulic pressure can come in for the pressure sensor to be able to sense that. Um, and then, but we note that, so when we went to, this was kind of on the longer side of a deployment, especially relative to SAG-D wells, which are typically much shallower and often shorter. And so when we went to pump the silicone gel, it was highly viscous, and we reached the maximum pressure of our pumps, pumping uh, the silicone gel into the strain sensitive fiber. So that resulted in only the bottom third of the capillary tube that had our strain sensing fiber being filled with the gel. And the top 2/3 were filled with nitrogen or a nitrogen air mixture. And so that was not ideal, but time constrained us. We had a schedule to meet with the circulation test, um, and so we had to go with that. We've since come up with methods that we think we can get that strain fiber, the viscous gel, fully filling that capillary tube. Um, but spoiler alert, the fiber ended up failing right at that interface. So um, we yeah, that was a lesson learned from this deployment. And then so we did have to modify the 16B wellhead to install this coiled tubing. So we added wing valves and then a coiled tubing hanger. So we don't have to have a coiled tubing unit out on location for the duration of the circulation test. You hang the coiled tubing in the wellhead, and it can be used for long-term monitoring. Okay, so that was kind of the design, and so now here's the deployment, a picture of the installation, and then we wanted to land the end of the coiled tubing past the final perforation, but then just for risk reduction to stay out of the open hole section of the 16B. And so we did land the end of the coil right at 10,100 feet measured depth. And then this is what the 16B well looks like now with the coiled tubing strings, with the coiled tubing and then the capillary tubings containing the fibers and the tech line protruding from that. So some just operational lessons learned. So the 16B had pressure on it, and we didn't want to kill the well, and so we had to do a stripping operation. And so I'm not going to go into too much detail on this, but you require this special piece of equipment called a work window that allows you to run the coil, and then when you're ready to land it, you close the BOPs, open, bleed off the pressure up here, insert the slips into this work window, close the work window, reopen the BOP, and then land the coiled tubing in the wellhead. And in our paper that we presented at Stanford on this, we detail some of these operational notes. If you're ever trying to go do this on your own well in an enhanced geothermal system. One of the lessons we learned is the coiled tubing company that deployed the coiled tubing, they measured the weight versus time, but not depth. And they did not digitally log the weight. They had a manual when I found that out, I started sitting in the van and I would have them call out the depth we were at various loads. And so, um, uh, without dwelling on this too long, when we were running in, we did encounter some high friction in the deviated parts of the well. In fact, we completely stacked out the string in the perforated interval between 95, 80, and 10,000 feet. And so that could have just been done due to deviation, or it's possible that we had some sand accumulated in that portion of the wellbore that was holding us up. So we're actually currently working with a coiled tubing company to model this and see if we think we were encountering sand or if that was just our expected frictional profile. And then, okay, so yeah, as I mentioned, the strain sensitive fiber. So actually, all the fibers were healthy when we landed the coil. So we landed the coil in the wellhead. We took OTDR traces, and they all looked good. But then the next morning, after there was, I guess, sufficient time for the well to thermally equilibrate, the strain sensitive fiber was broken, where we estimate right at that. 2/3 of the way down, right at that interface. And so our hypothesis is that silicone gel was expanding due to thermal expansion, and that the fiber, it was just getting buckled, and then we broke it, is what we understand happened. So the fiber is actually still reading on the first 2/3 of the well, but not in the bottom whole section. But we still had our other single mode and multi-mode fiber, and we were able to get all the measurements that we wanted for the circulation test. So that was the design and deployment of the coiled tubing string, and now I'll talk about our circulation test we did, the measurements we got from this coiled tubing string, and then and some kind of lessons learned or maybe some observations about this enhanced geothermal system. So this is a aerial shot thanks to Leroy. During our circulation test, we were injecting in this blue well, the 16A, producing from the 16B through a debris catcher. We metered the flow using a turbine meter. We had a tracer sampling point here, and then there's a choke that we use to keep the well producing in single phase liquid. But downstream of the choke, we go to this geothermal separator. The steam is vented, and the remaining water is dumped into this sump. So this work, we're presenting the August 2025 circulation test, not to be confused with the August 2024 circulation test. So our circulation test was 7 days, where the 1 year prior Forge did a 30-day circulation test, and our test was shorter, which we're seeing maybe more transient effects, but it's neat to be able to do a kind of 1 year later time lapse, and we really designed our 2025 experiment to try to mimic the 2024 experiment as much as possible to facilitate a comparison for how, if at all, the enhanced geothermal system has changed a year later. Our fiber optic system was maintained its integrity throughout the duration of the circulation test. We both did tracer test. We added reversible absorption tracer tests to try to estimate the heat exchange area. I'm not going to talk too much about that part because we're still getting results from that. In this case, both times we had surface measurements, but this was the first time we're having the downhole pressure and temperature measurement during the circulation test in the 16B. And then, yeah, so very similar tests. And here we go. Here's for the 7 days we were circulating, and then a 1 day fall off period. We're presenting the 16A injector pressure in red, and the injection rate in blue was 10 barrels a minute throughout all 7 days. The 16B pressure here in yellow, initially we had the well shut in. We wanted to try to recharge the reservoir before opening the well. And the agreed upon criteria to avoid hitting a fracture gradient was we wanted to open the well before it got to 1,000 psi. So we started flowing about halfway, 12 hours after starting injecting. And then we flowed for 6.5 days at a production rate that started around 3 when we first opened the well, and increased to around 6.5 by the end of the 7 days. Each of these kind of discrete drops in the 16B pressure are when we made a choke adjustment to open the well up to additional flow. So we really wanted to maintain single phase liquid flow so that we could get accurate turbine meter measurements. Okay, so this is a plot of the 16B surface temperature versus our injected volume. In gray, we're showing points from the 2024 circulation test, and in black, we're showing measurements from the 2025 circulation test. So a very similar trend. However, I just got this picture showing that in the first 2 days, maybe, we realized that the thermocouple probe was not fully protruding into the flow stream. And so I went to the hardware store and bought a bunch of insulation and wrapped it around. And that happened at this point, which really reduced the effect of the ambient temperature on the production temperature measurement. And so I think the main thing to note here is, we're seeing really similar temperature response between 2024 and 2025. And then probably because the 2024 thermocouple measurements were not insulated, the production temperature is maybe slightly higher than what we thought it was in 2024. Production efficiency. So this is a plot. Basically, it's just on the y-axis is our production rate divided by our 10 barrel minute injection rate. And on the x-axis, I'm plotting this as a function of the stored volume in our reservoir. So the injected volume minus our produced volume. So we were injecting at 10 and producing only at 5 or so, much less than that. And so as time went on, we had more and more stored volume in the system. And here I'm in green are the data points that I most trust. These are measurements from the 2025 inline turbine flow meter that I pointed out on that picture. And then in black, what I'm showing is we also had 2 turbine meters downstream of the downstream of the geothermal separator. So the geothermal, when fluid exited the choke and went into the geothermal separator, steam flashed out the top, and we had some remaining liquid dumping into the sump. And one of the reasons I don't trust these measurements very much is they should not be higher. We should not have higher water volumes coming out of the separator than we did when everything was single phase liquid. But I'm plotting them as a comparison to the 2024 separator-based Utah Forge measurements, because I think that it's a better apple-to-apple comparison. And I think the last thing what we can see is that as we have more and more volume stored in the system, our production efficiency increases. We're producing closer to our injected rate. And I wish that I felt like I could make a conclusion based on, okay, maybe our fracture system got bigger over a year, because in 2024 we were seeing higher efficiencies with less stored. For the same stored volume, we were seeing higher efficiencies. But I'm not super confident in the comparison of these flow meters because the um, the measurements coming out of the geothermal separator, you've got gas that's still flashing out. You have scale coming out of that geothermal separator that is also influencing the turbines, and you have a time delay effect with based on the liquid level that is in that geothermal separator. All that to say is I think it just going forward in Forge, I'm excited to compare these measurements in green to the long-term circulation test that's going to be conducted this year. And I also just kind of want to put a call out to uh, the Utah Forge team and everyone involved that I think this is a very important measurement to get right because a lot of modeling is based on this. Um, and so, yeah, I'll just move on from him. Okay, so we ran a spinner uh, production logging tool in the 16A during injection. Um, and we're comparing the results from August 2024 and August in 2025. On the right here, I'm showing from Chris Fred a schematic he put together showing okay where the stages are in the 16A, and you can see that the stages vary in terms of the number of clusters. So stage 8 and 9 had a large number of clusters. Stage 10 just had a single cluster. Um, and then there's an open hole section in the 16A, and then there's a few single stage or small cluster stages in stages 7 and below. Stages 6 and 7 were non-propped and did not take much flow at all in either test. But I think the interesting thing to note here is how much less fluid was going into 3R, the open hole section in 2025 compared to 2024, and how much flow that single cluster stage 10 is taking. In 2024, that was about 25%. In our test, it was stage 10 with that single cluster was taking almost 50% of the injection profile. So if we have runaway highly conductive pathways between the wells that are short circuiting this flow system, that's not going to be good for our long-term heat sweep performance. Stages 8 and 9 seem to kind of flip-flop between the tests. Now and okay, so why am I, this is another plot where I'm also showing the injection flow distribution, but I'm also including that from April 2024. And in April 2024, they were not able to get the injection logging tool below stage 7. So 6 and below are all kind of lumped together here. But there's a really interesting trend looking at all three injection logs. Stage 10 is taking more and more fluid, and the toe of the well is taking less and less. Um, All right, so now to get into some of the fiber optic data, I mentioned that when we made a choke size adjustment here, we would get uh, we were doing that to manage pressure, and we'd get a quick pressure drop and an increase in flow rate. And whenever we did that, we would observe these thermal slugs in the 16B. So this is a plot of depth along the y-axis, time along the x-axis, and the color corresponds to a change in temperature measured by the fiber optic cable. And these are actually Nubrix's RFS, DSS, Raleigh frequency shift based measurements. They're sensitive to strain and temperature. But what we're interpreting this as primarily a temperature change. And so you can see that these we have little slugs of hot fluid entering the well and then traveling up the well. And so we can see an inflow at stages 5, 4, 2, and then from below our perforations in the open hole section. And I have a student who has done numerical modeling, but also come up with a pretty simple analytical solution to take the slope of these thermal slugs and infer a production log from them. So we just presented the injection log on the 16A. Now we're using our fiber optic measurements to interpret a production log on the 16B. And so we're comparing our thermal slug-based production log to the spinner production log that was run in 2024. And so in 2024, they could not run the tool below stage 3, so they had to lump the open hole, stage 1, 2, and 3 all together. And if you look at this in kind of the lumped terms, the results are really similar. So 70% of the flow we indicated was coming in through stage 4 and 5, and that agrees pretty well with about the 2/3 estimated in 2024. And then we're estimating a total of 30% of production coming in from the open hole, and then stage 2. We did not see those thermal slug signals at stage 1 and 3. It's possible that we were getting inflow in stages 1 and 3, but there was just no thermal slug signal initiated. But our current preliminary interpretation is that this is the flow distribution. So it's interesting to note that 2 stages are maybe not contributing any flow. And it's interesting to note that the production log seems pretty similar from one year to the next, whereas the injection log has seemed to change so much. So maybe this is telling us something that, the 16A, where the fluid is coming in to multiple perforation stages, is connecting to similar fracture networks in the far field. So it doesn't matter if we're still trying to come up with a kind of table of key observations that we can use to map this fracture system and honor all of these different measurements. But we think there's some complexity between how stage intervals in the wells actually connect to the fractures in the system between the wells. Okay, so this is a plot of the DAS acoustic noise. These depths are not zeroed to surface yet, but you can see these bands right around here, which when you shift it, it corresponds to stage 4 and 5. So we think we're hearing noise associated with inflow from perforations in stages 4 and 5, and those were pretty constant sound bands throughout the duration of the test. Okay, another interesting thermal slug observation. So I mentioned that when we started injection into the 16A, the 16B was shut in. So this plot is showing thermal slugs while the 16B was shut in. And instead of hot slugs moving up the wellbore being produced, what we're seeing is thermal slugs that are moving from a shallower part of the wellbore deeper and cooling the well. And so we see inflow from stages 5, 4, and we think this is stage 3. And these thermal slug signals stop at stage 2. We're not quite sure if they're stopping at stage 2 or if they're going all the way down in the open hole section. We need to do a little more analysis on that. But our interpretation is that when we're injecting into the 16A, there are these highly conductive flow pathways to stages 4 and 5, and that it is actually recharging the that fluid comes in quite easily to those stages 4 and 5, and then it's recharging the reservoir through the 16B toward the toe of the well. So we would generally make the observation that the heel of the 16B is much more well connected to the 16A than the toe, and we're wanting to come up with more quantified interpretations of this in the future. We also injected some tracers during these tests, very similar, and that analysis is really still forthcoming. But we did see similar responses where the tracer response could be modeled as two dominant flow pathways in the system, one with a fairly shorter residence time and the other with a longer, more diffuse residence time. In this, so if we go to the average residence in barrels, we see one component has an average residence of about 6,000 barrels, where the other one has a higher. Okay, that's kind of the end of what I have on the circulation test, but one final note is that DAS was recorded during stimulations conducted by an offset operator, and the fiber optic cable was actually able to pick up microseismic events through the coiled tubing during this offset stimulation. And I show that just to kind of help wrap up our conclusions here, that this instrumented coiled tubing was able to provide valuable temperature, strain, acoustic, and then bottom hole pressure measurements. And we were able to detect thermal slugs to use for production logging. We were able to see microseismic events through multiple layers of a wellbore completion. We have some lessons learned from the coiled tubing installation, such as make sure that the coiled tubing company has a depth counter on their string, and you can read more about that in our paper, but that our strain sensitive fiber failure shows that these continue to need future work. Regarding the circulation test observations, there are both similarities and differences that are in the results. The injection profiles are somewhat similar, yet with stage 10 taking more and more over the time, and the open hole in stage 3 taking less and less over time, while the production profiles seem quite similar. And then our crossflow indication, just indicating that the heel of the 16B is much better connected to the 16A than the toe. With that, I'll stop talking, and thank you very much for the opportunity to speak with you, and I'll take any questions.
Thank you, Smith. That's a fantastic presentation. You do have you do have several questions in the chat, and if you can't see them, I can read them. So the first one is from William Harbert, and William is interested on slide 18. What does the negative weight mean, and what are its implications?
Yeah, so slide 18, the negative weight. Let me go to a picture of this. So the coiled tubing unit has something called an injector. And so this has some grips on it that is actually able to push the coiled tubing in. It kind of looks like tracks on a track hoe that go around and grip that coiled tubing and push it in. And so when the weight goes negative, that means the coiled tubing is not falling into the well under its own weight. We're having to actually push it in, which means that's why we said we think this could be an indication of sand that's accumulated in the well, the high friction interval that we're having to push this coiled tubing through.
And then the second question is from PF Rue, And PF is interested in why does the attenuation profile seem to change over depth on the OTDR plot that you showed? And how do you explain those losses, the huge loss close to the surface and the other smaller loss events deeper midway, smaller loss event deeper midway?
Yeah. So, the great question. The first thing to say is that these losses close to the surface are related to different surface terminations. So, you have to splice the fiber. After we ran the fiber in the well, we bring it to a junction box where we splice it, and so there's some losses. You get high reflections at those splices, and then you also get losses associated with that. So that kind of gets us to here, and then we've got in the first, let's say 900 meters of the well, a fairly normal OTDR trace, but then we do have a loss event around 950 meters that I would have to get back to you on that. I'm not sure what we think that might be due to. But then the major loss point here is where we think the fiber just broke due to the expansion of that gel.
Okay, great. And then the next question is from Leopoldo. Can you comment why the pressure fall off in 16A is so slow when pumping is stopped? If both wells are connected with fractures, I was expecting this fall off could be faster.
Um, in Okay, so I think uh, the question is related to the pressure response right when we shut in at the end of the circulation test. And I think the first thing to note is that I I think the way I look at it is that the wells are equilibrating in their pressure. So right when we shut in the 16B, we very quickly pressure up to um, 1400 psi or so, but we still have a higher pressure on the 16A. So maybe one way to think about this is when you're injecting into the 16A, you have a higher pressure region around the 16A, and you have pressure losses as it flows to the 16B. When you shut both wells in and stop flowing, then that pressure is going to try to equilibrate. And so you can see those pressures coming and almost joining each other. I'm not sure we would expect them to be the exact same because of differences in density of of the fluids, because we had the 16B was a hotter well than the 16A, but that's how I interpret the pressure response here. That's a good observation.
The next question is from Con Wu, and Con is asked, based on the thermal slug response in 16B, what is the production distribution among stages 8, 9, and 10? How does the thermal slug behave over these stages?
Yeah. Hi, Dr. Wu. The To clarify, the fiber optic cable is in the 16B wellbore. And so in the 16B wellbore, we have an open hole section in stages 1 through 5. So we're measuring thermal slugs in the 16B. To connect the production, but kind of, if we can, that's actually our goal, is if we can kind of allocate, we have this inflow distribution from the spinner uh, log on the 16A. And if we can allocate, okay, how is the fluid from stages 8, 9, and 10 getting to stages 4 and 5, or whatever stages they're getting to on the 16 be. And your work, Dr. Wu, and your students' work at the Stanford conference was really great, providing a map of some possible pathways between the wells, and we certainly want to build on that work.
Okay, and Jonathan Aho Franklin. Jonathan has a technical question. What IU was the microseismic gathered from?
Yeah, that was Nubrex's DAS unit. So I forget their name of it, but uh well actually um I think that was this microseismic event came from the offset operator who had hooked up their box. So you probably know better than me on that. That might be an IDAS V2. Um, but yeah, so the offset operator was recording on during the offset stimulations, and I think, uh, as I understand it, that data will eventually be made publicly available. Um, but we also did record DAS during our circulation test with uh, Nubrex's unit, and uh, yeah,
And the final question, or final for now at least, Jean Alcouri he wants to know on slide 24, the 0.6 production efficiency seems fairly low. Any idea where the fluid is going? And maybe
yeah,
we'll start with that. He's got two more questions.
okay, um, yeah. So I think that the what's encouraging is that the trend is still upward and almost linearly upward with this stored volume versus production efficiency. And so I think and that the trend from 2024 would show that that continues out to more and more stored volume in the reservoir. So the how I interpret this plot is we are still reaching a steady state in our flow paths in our enhanced geothermal system. We haven't reached steady state yet.
The Jean's second question was, did you see any pressure measurement indication of recharging at nearby wells?
Nearby wells. So that's a good question. John, do
I
you
can
know if
actually, yeah, yeah. After stage 8 of the stimulation of the injection well, there was a pressure signature at an offset well known as 5832, and there is some communication between 16 the injector well, the production well, and this offset well. And then, so Jean's final question is, you mentioned fractures getting bigger compared to the 2024 test in relation to the decrease of production efficiency. What mechanisms do you have in mind?
Yeah, that's an interesting question. So one possibility is that the fractures are extending and the fracture network is getting bigger. Another possibility, but not mutually exclusive, is that we've been producing a lot of salt. So Stuart Simmons and Clay Jones and the University of Utah team have a lot of great work showing that the produced water is has more total dissolved solids than the injected water, and so it seems that that is one of the key observations that says perhaps we are connecting to some natural fractures that were filled with salt. And as we produce that salt, there's now more empty space in that fracture network, is another possibility. Yeah.
Um, well, that's the questions, and unless anyone else has a pressing question, or they can reach out to Smith directly. And a really forward-looking technological development. I think congratulations to you and your team.
Well, thank you so much for the opportunity, John. And thanks to everyone for joining.